Hey guys, so in this video I'm going to be going through the 2021 scholarship physics paper, but I'll just do the mechanics section because of time restrictions. So yeah, let's get right to it. Um, okay, cool. Question 3 about a ball. Um, so they've given us a double angle formula here, so we're probably going to need it somewhere in the question, but we'll use it when we come across it. So a ball with mass m is launched at speed at an angle theta to the horizontal as shown, and the projectile lands at the same height that it was launched from. And the horizontal, okay, I should probably highlight that. Oh wait, I think I've got a highlighter in here. Hold on. Yeah, there, that's much better. Um, and the horizontal distance g is maximum when theta is 45. So we just show. And we can assume drag is negligible for this part of the question. Okay, cool. So let's start by just drawing like a really quick diagram to show how it goes. But basically, you're gonna have some ball launched with some velocity v at some angle theta, and it's gonna have a vertical component to its velocity because that's what the question wants you to do. You consider the components of its velocity, Vy and Vx, right? And it's going to be traveling in this like negative parabolic path, right? And at this point here, it's going to be at its maximum height. And so what that means is that the vertical velocity is going to be 0 meters per second, right? Um, because it's not moving up, nor is it moving down. If we only analyze the y-axis, of course, the x-axis will be moving at a constant speed because we assume that drag is negligible. Therefore, it will just remain in motion unless it acted upon by an external force. And using the sine and cosine trig relationships, we can write both Vy and Vx in terms of sine and cosine respectively and also velocity. So that becomes Vy equals V sine theta and Vx is equal to V cos theta. And because we know that the projectile lands at the same height that it was launched from, if it's positive Vy at this point here, then I know that as soon as it lands, its vertical velocity will be negative Vy. So the first thing we need to like sort of find out is how long does the ball spend in the air. So selecting this equation here and rearranging it for time gives this expression here. And now subbing in our numbers, I know that my final vertical velocity will be negative Vy, right? So negative V sine theta. And my initial vertical velocity, which is here, is going to be V sine theta, but it'll be negative V sine theta according to the equation, all over negative G because we're accelerating upwards. And so simplifying this gives our total time spent to be 2V sine theta over G in this theoretical situation. And our next step is to now find the horizontal distance because that's what we need to find and show. So dx is equal to vx times time, right? And our horizontal velocity was v cos theta times 2v sine theta on g. And simplifying this, we get 2v squared sine theta cos theta on g. Now, notice how we've got a 2 sine theta cos theta. We can actually use that double angle formula that they gave us earlier and simplify this expression and write that dx is actually v squared on g times sine of 2 theta. And now they want us to find maximum horizontal distance, and that occurs when theta is 45. So let's just write when theta equals 45 degrees, dx is equal to v squared on g times sine of 2 times 45. Simplifying this gives dx equals v squared on g times 1 because sine of 90 in degrees is 1. And therefore, that is this first question proved and shown. So yeah, let's move to the next one. A more accurate model of the situation includes a drag force, F, and it changes the motion of the ball, and a simple assumption is that the drag force is constant in magnitude, and it acts only in the horizontal direction. And we need to show that now this new horizontal distance will be given by this expression if we take into account the drag force, from what I understand. So let's write the acceleration, right? Like on the x direction, the net acceleration it'll experience from this drag force will just be negative f on m, as f equals ma. And what else? Because horizontal direction, well, we can write vx equals v cos theta. And I also know that the time it spends is 2v sine theta on g, right? Um, and we're trying to find distance. So based on the variables we've got here, I think the ideal equation in this case would be d equals vi t plus half a t squared. Um, and check this out. So this vi t component actually will end up becoming v squared on g times sine of 2 theta because that's literally what we did to find the horizontal distance, right? We did velocity times time, and we're dealing with the same direction here, which is the x direction. And so therefore this would just become v squared on g times sine of 2 theta. And now we can start doing the direct substitution into half at squared. So that would become a half, then negative f on m. Actually, I'll just rewrite that. Plus, actually, no, that would just become a minus f onto m bracket, and then t equals 2v sine theta on gravity squared. Simplifying this expression, right, we'll just give this bracket here, minus f on 2m into 4v squared. Okay, so this 4 and 2 can cancel, and so this will become f on m, and this will become a 2v square sine squared theta on gravity. And then now expanding this expression here, we get dx equals v squared on g times sine of 2 theta minus 2f v squared sine squared theta on mg squared. Now, taking a look at the two terms, you can actually factor out the v squared on g, yeah, because that's actually common. So we can just write dx is equal to v squared on g bracket sine of 2 theta minus 2f on mg times sine squared theta. And that's the v squared on g sine 2 theta minus 2f on mg sine squared theta. And that's proven. So yeah, that's that one done. Cool. C, discuss the validity of the assumptions about the drag force in part B. More realistic assumptions about the drag force, and explain how these would affect the horizontal distance. Okay, so I'm just going to do this in bullet points. But the first thing I picked up was that actually this drag force would not only actually act in the horizontal direction, but rather it would act opposite to the velocity of the ball. So let's make that our first point, is that, like this is a realistic assumption. So the direction of the drag force, let me just move this over this side. Drag force would always be directly opposite to the direction of motion of to the direction of motion of the and we should also, yeah, okay, that looks like that's fine, and that should, yep. And the next thing I picked up on was that they assumed that the drag force is constant in magnitude. However, in reality, this drag force F would actually be proportional to the velocity of the ball. Um, Therefore, actually, um, this changing drag changing drag force would change the velocity of the ball over time. Or in other words, like the, the drag force is not at a constant, is not a constant, is not at a constant magnitude. Um, and so as a result, this will decrease both vertical and horizontal components of the ball, and hence it will spend less time in the air. Okay, that's quite a long answer. I should have actually used some of the extra space at the back, but I can't be bothered scrolling down. So I think, yeah, it'll spend less time in the air and not go as far. Okay, we're actually kind of going to the second question here, but yeah, that's I think that's about it for this one. So it won't like go as far. All right, yeah. So let's move on to this next, yeah, the next question D here. So after receiving an initial push, the solid ball begins rolling up a slope as shown on the right. The ball has mass m, radius r, and a moment of inertia 2/5 mr squared. Keep that in mind. And when it is at height 0, the center of mass of the ball has some velocity v initial. Okay. Assuming that drag is negligible in this situation, show that velocity or the center of mass of the ball when it... Okay, so I'm gonna do this the conservation of energy way. So initially when the ball is here, it would have a linear kinetic energy. So it would have EK linear plus EK rotational. And because it's at height h equals 0, the mgh term would just go to 0. So that's all your energy initially. But this would change into EK linear. This would also become EK linear. I'll explain further why, but as well as EK rotational, but in addition there will also be potential energy EP because it's gaining height, right? So this is how the conversion of energy that will take place. Because you're going upwards, you will be gaining potential energy. So now let's put this into equation terms, which should be a bit easier to understand. But basically, we're going to have half mvi squared plus half I omega I squared, right, is equal to half mv squared plus half I omega squared plus mgh, right? Or they use lowercase h, so right h. So basically when it reaches here, it'll have some velocity v. As you can see, as indicated by this arrow, indicates that the ball still has some velocity v, and as long as it's got a velocity, a linear velocity, the ball will also have a rotational kinetic energy. Um, so that's our formula here. We should also use the relationship v equals r omega and make the substitution that omega equals v on r, and similarly omega I equals vi on r. So from here we can go ahead and start making our direct substitutions. So this is going to get pretty messy, I guess, but anyways, let's go right in. Try using a different color maybe to changing blue. Yeah. Okay. Half mvi squared plus a half bracket, and then our inertia was, I think it was I equals 2 over 5 mr squared. I'll just go double check. Yeah. Um, and then 2 over 5 mr squared times by omega is v on r, so v square on r square is equal to half mv square. This should actually be vi squared, half mv squared plus half I, no, half bracket 2 on 5 mr squared. Omega is v square on r square plus mgh. Okay, so now we can start simplifying. You can cancel the r squares, so this will now become half mvi squared plus 2 on 10, which is 1 on 5 mvi squared is equal to half mv squared plus 1 over 5 mv squared plus mgh. And that should be a lowercase h also. Cool, now we can start. Oh, wait, mass is common in every one of these terms, so I'm actually gonna like entirely get rid of the mass. So we'll get vi squared on 2 plus vi squared on 5 is equal to v squared on 2 plus v squared on 5 plus m plus gh. And then 5 plus 2, 7 on 10, 7 on 10 vi squared. I'm actually gonna like swap the equation because we're trying to look for v, so 7v squared on 10 plus GH is equal to 7VI squared on 10, right? And then multiplying both sides by 10 and dividing by 7 will give V squared plus 10GH on 7. Oh my god, why do I keep writing capital H? Is equal to VI squared, and coming over here, then we can write V squared, oh my god, V squared is equal to VI squared minus 10GH on 7. Therefore, V equals the square root of VI squared minus 10GH on 7. NGH on 7. And yep, that's proved. Sweet. Okay. Yeah, so that's that one there. Cool. And the very last question here asks us to give us an expression for the maximum height reached by the ball as it rolls up the ramp. So the maximum height means that its final velocity, or v, will be 0. So if v equals 0, right? So let's just write that out. Max height occurs when velocity equals 0, and this minus 1. Therefore, square root of vi squared minus 10gh on 7 equals 0. Squaring both sides and taking the 10gh on 7 to the other side gives us the expression that 10gh on 7 is equal to vi squared, and therefore rearranging this equation for height gives height equals 7vi squared on 10g, and that is my final answer. So that is the scholarship physics, entire scholarship physics question 3 done. I hope that helps, but yeah, thanks